Alrighty, so let's get into it. So process management, even more fun stuff. So after we fork, how do we follow up on the fork and actually manage our processes? So first, let's dive into that exec.ve example because that's another important thing to know. How to replace this process with another process. So here is some code, probably easier to show that. Again, we have main. We're going to printf some message. Just should hopefully always print. And then we'll set up an array of char stars or an array of C strings. And the first argument is going to be ls, then null. So the definition is that it knows when the array is over when the last element is null. So we have argv, and then we have env, which stands for the environment variables. Since I don't care about them, I'll set them as null. And then this is the system call that, well, this is a wrapper to the system call, but the system call is called the same thing. This is called exec.ve, and it will take as the first argument the path of the program you want to replace this process. So if this is successful, the kernel will go ahead, load that program into memory, figure out where it wants to start executing, and start executing it if it's successful, and it would give it these arguments and this environment variable. So we have two options. If this is successful, it will actually just run ls and do ls things. It just runs ls. This process gets replaced. So this process would have the same PID or PID, but now it's running something else. So if it's successful, if this call is successful, nothing else will execute because this process got replaced. Now, if there is an error, so it's defined that if you look at the documentation, if this returns -1, it means there's an error, and it sets this global variable. Well, if there's an error, I'll just store it in this variable because it actually, this p error will also interact with error no and may change it. So I want to report the first error that happened. So I'll use this to print an error message. It's a wrapper that will give you a human readable error no, so you can actually read what was going on. And then the process will exit with whatever the error number was that we got. And then in either case, this line will not print because either exec.ve worked and this process got replaced, or there was an error and it reached this return statement and exited from main. So there's no way this line will execute. And you can see if I run it, it says I'm going to become another process. And then it does the same thing ls does. So it shows me the contents of the current directory. So that is how you run another process, or sorry, how you run another program on any Unix system. So you can tell now that, hey, when your shell wants to execute your process, well, it would fork itself, and then likely in the child, it would just exec.ve your process. That's why we see even that hello world example, when we straced it, the first line was actually exec.ve. So that was not from us. That was from your shell actually executing it. So that's where that came from. OK, so yep.
Sorry, could you explain what the arguments of exec.ve do again?
So the arguments of exec.ve, the first argument here is like the full path to the program you want to execute. On Linux, it's going to be like an ELF file, right? And then this argv is essentially the argv you get from main, right?
So you just make it every time? You just have to put the program name for the argv?
Yeah, so you'll notice that this ls name like doesn't actually correspond. I could have named this whatever I want. Like, actually, let's go back. What is it? So it still works the same. It's just a convention that the first argument in main is supposed to be the name that the user typed to run your program. It doesn't have to correspond with the name of the actual program or vice versa or anything like that. In fact, what is it, ls help? Yeah, so usually when you type help for something, it says usage ls whatever. Well, say if I want to do ls help, I'm giving it an argument. So if I want to actually run it, I could do something like that. So you can tell what your shell is doing. It's splitting what you type into different C strings and then passing it to argv to actually execute your program. So if I do something like this, this will be fun. Well, now it's printing out the help message for ls because I gave it the help argument, and that program's going to read it and do something with it. And funnily enough, you'll see where it actually uses that convention. You see usage. So in part of the usage message, it's supposed to tell you what you type to actually run the program. The convention is the first argument is supposed to represent what you actually typed. So it doesn't have to match up with the program name at all. In fact, look at the name, right? So, yep.
So do the arguments get passed in both like at the same time, or is it first like WTF and then that'll execute first and then dash that help work?
No, so these are all the command line arguments to your program. So like if my main, had int argc and argv whatever. So they line up exactly with those arguments to main. So when ls runs, it would run its main, and in this case, it would get 2 arguments. The first one would be ls, the second one would be help. Yep.
What's the exec and the third argument?
The third argument's environment variables, which we don't really get into in this course, but it's essentially like, you can think of they're like global variables for processes that the operating system kind of keeps track of. Okay, so let us blast through some content today and then get into more fun examples where we break stuff. So you might notice whenever you use Linux, the terminology I showed you before is a bit different than what you'll actually see on Linux. So some of you have already played around with the proc file system. So if you go read the status file in lab 1, you're using name. Another thing you could look at is the state. And again, everything in the proc directory that has a number represents a process. There's actually a special process called, or a name in that directory called self, which refers to whatever process is accessing the proc directory. So if you want to figure out what your process ID is, you could read proc self status or something like that. And that's basically what git pid does. So yeah, so on Linux, it represents running or runnable as the same thing, which in the state diagram is pretty much the same as running or waiting, which also meant ready. So Linux doesn't really differentiate between the two. And then there are 2 types of block states. There is interruptible sleep and uninterruptible sleep. Interruptible sleep means it's doing something, but you can wake it up and kind of prod it to do something else if you really want. The details of that get a bit, we won't go quite into those details in the course. Just know you could prod it and it could react and do something. Uninterruptible sleep is like it's waiting for I/O or it's waiting for network, and it's something that even if you poke it and try and say, hey, do something, it will not wake up and it will wait for that operation to continue. You can't get rid of this process in any way, shape, or form, and it's kind of annoying. Then there is a stopped state that is, we'll get into signals hopefully in the next lecture, but you can actually tell a process to stop executing, and you can control whether or not it executes or not, so that's what that represents. Then you might see the Z state or Z state for zombie. That's a fun name. So keep that in mind because we'll be talking about zombies today. So you might also ask the question, well, if we have parent and child relationship for every single process on our system, how does it ever start? So that is a good question. The entire user space on Linux starts with the kernel as a hard-coded thing. It launches process ID 1. And process ID 1 is responsible for launching every other process on your system. So as part of booting up, and when the kernel is done initializing all your hardware and everything like that, it will start one and only one process. That will be called process ID 1. And as long as that process is running, well, then your computer is running. If that process is not running, your computer is no longer running. So it's responsible for launching every single other process on your system. It might not launch it directly, but it is going to be the ultimate grandparent, if you want to think of it that way. So it is called a NIT, and again, responsible for launching every other single process on your machine. It can delegate that work to some of its children, but no matter what, that's going to be your ultimate ancestor. Specifically, the software on Linux is called systemd, but there's lots of other options. If you wanted to yourself, you could write your own init, and that would be fun. So you could write an init that just launches the shell if you only want shell access, and then you only have one shell. Things like that. You have as many options as you want. On some operating systems, there might be like an idle process that the scheduler can run along with a init to represent like your CPU's not doing anything. You might see that on Windows where there's like an idle tab in Task Manager. So this is what a typical process tree would look like. Since we have parent-child relationships, there is that relationship between every single process. So it would look something like this with the NIT at the very top. So the direct children of a NIT might be some system services we don't really care about, but they're called like journald, udevd, which kind of deals with hardware. Then it might launch systemd, a user version, to represent your logged in user and manage all the processes for your individual user. Then, we might open the terminal. So that would be another process. So your terminal would be a process, and within it, it would have your shell. So your shell would be another process that your terminal launches, and then you would launch something from your shell like htop, which we'll see, and then this GNOME shell, well, this is your whole user interface, the process that represents your whole user interface. So if you launched a web browser, it would look like this. It would just be a direct parent. And then your web browser might have many sub-processes in it. So it might have many children sub-processes, which looks a bit weird, but in fact, all the browsers are architected this way, where every tab is actually a different process, because since every process is isolated, if one of the tabs crashes, it doesn't bring down your entire browser. It just destroys that one tab. So Chrome will follow that architecture. Firefox will follow that architecture. And that's a handy thing for processes. Yep.
Sorry, could you quickly explain the difference between a terminal and a shell?
So the terminal is what you type into. So it's like the window that you see. So it's responsible for translating your key presses into bytes and then translating things that come from like standard out into characters you can actually see. So it's doing all the graphical stuff. And the shell is just taking what you write in and then executing programs and stuff. Yep.
If you were to kill an intermediate process, would it kill the rest of processes as well?
So they are independent. So we'll see that today. That'll be fun. Yep.
Sorry, do you see that the GNOME shell is basically like when you open up your virtual machine, that entire thing is in GNOME?
So when you log into your virtual machine, if you installed a desktop environment, specifically the GNOME one, the whole user interface, like your desktop, is called GNOME shell. So that represents, sorry? Yeah, it's like your primary interface for that. So everything you see will be GNOME shell. Yep. All right, so how you can see the process tree on your virtual machine, you can use htop. If you press F5, it will translate all the processes you see into a tree. So we can see that real quick. So if I type htop and expand it a little bit, it'll give me some information about my CPU usage up there. And then you can see that F5, uh-oh, my key doesn't work. Tree. Oh, okay, so now you can see it's a tree view. So at the top, there is a init, and then you can see it has lots of direct children, all of these that do a lot of things, and it goes on, and then you can see, hey, here's my SSH session. It's a process. I can see that this is me logged into it. There's some words I can't understand, but eventually SSH launches ZSH, which is my shell, and then here's bash, so it's running bash. That might be a different session, but you can go through. This is an actual tree of all the processes running on your machine, and you can go ahead and explore that. You can see what VS Code is doing. There's VS Code's terminal, so it launches the shell as well, and here's the command that I'm currently running. So you can see where it lives in the hierarchy. So if you want to experiment and go around with that, that's lots of fun to do, but everything has a parent. Yep.
How does numbering work? Like, what if it jumps from like 1 to like 300?
How does what work, sorry?
Numbering for the process.
The numbering.
Yeah.
Oh, so the question is, how does the PID numbering work? So in practice, it's pretty much sequential. Like, it just assigns 1, then 2, then 3, then 4, then 5, and then it won't reuse them until it comes back again. That's generally how it works, but theoretically, it can just assign any free number when that process starts, and the only rule is it will stay that number across its whole lifetime. After it's done, it can reuse that number. But typically, you'll just see it go up sequentially. Yep.
Just because the process IDs are sequential, does that mean like the virtual or even the physical memories that the processes are assigned to, they don't have to be sequential, do they?
So the question's about virtual memory. We'll get into virtual memory later. Don't worry about virtual memory for now. Yeah, that's a whole other can of worms we'll get into. All right. Oh yeah, hey, there's a slide for it. So processes are assigned a process ID on creation, and it does not change for the entire lifetime of that process. So as long as it's active, it's that process ID, won't change. So most Linux systems, it goes to a maximum of like 32,000, and then 0 is reserved for invalid. That's how the child knew what the child was, so 0 is just not used. The first magical process is 1, 0 is just invalid, and eventually the kernel will recycle them after the process dies for a new process. Maybe you never reach it to 32,000 and it doesn't recycle them. I think now the limit is even larger than that, and the Mac limit is different than that as well. So you might see different behaviors based off the kernel, but they'll always follow the golden rule of you assign a process ID that's unique to a process while it's running, stays the same for as long as that process lives, and then when it dies, you can go ahead and clean it up. And each process has its own address space. You might hear that term. That basically just means it has its own virtual memory. So whenever we say a process is address space, it's the same thing as its virtual memory. So its view of memory that it has, which is completely independent, and it thinks that it's full control over memory. All right, so previously, you might have noticed in my example, I had a little sleep to make sure that the parent exited last. You might have asked the question that what happens if the process exits first and no longer exists? So you create a child, and then your child's doing stuff, and then you die. What happens to your child? Anyone guess? Okay, so one of the things we think the child also dies. Is that true in real life? No. So, yeah.
Just curious, like, why do you die before the child dies?
So, yeah. So the question is, why would you die before your child dies? So you die by just calling exit, and that's the end of the process. So your child could go do some calculation, some big long thing, and you could just do nothing. Yeah.
I mean, if the parent dies in the middle, like, nothing will happen to the child because it copied everything, no?
Yeah, so the child should still go on.
Does the child become an orphan process?
Yeah, the child essentially becomes an orphan. And again, this is where your Google searches get even weirder, because you might Google how to kill an orphan. Woohoo, that's not good. So let's get into the orphan processes. So the parent, like I said before, is responsible for the child. And what does that mean in terms, that sounds like a thing, but it doesn't mean anything quite yet in terms of operating systems. Well, what that means is that the operating system, like whenever you exit a process, you set an exit status, which is that number you return from exit. So as long as your process is exited, the kernel has to keep track of at least that number in memory. So it could get rid of all the memory that process uses, but would still need to keep its process control block around, because someone might have to read what happened to that process, right? So it has to be acknowledgement. So the minimum acknowledgement you have to do is read that process's exit status. So there actually is a step before or between when the process exits and before the operating system can completely remove it, and that's that acknowledgement. So if a process exits, most of its resources can get cleaned up, like memory, but its process control block will still be around, its process ID will still be around, and in that process control block will be its exit status, and the parent is responsible for reading that. So there is a system call to read that. Then after the parent reads it, then and only then the kernel can clean up all the resources that have to do with that process. So there's two situations, because typically your processes will not both end at the exact same time. So the first one we just kind of said, if the parent exits first, that is, the remaining process is called an orphan process. So it means that that child process no longer has a parent. So it is an orphan. Very, like, the terminology is not terribly great, but I guess it's effective. And then the second one is, if the parent's still running and the child dies first, that child process is called a zombie process. And why is it called a zombie? Well, because it's in like this halfway state between alive and dead. So it would be alive if it was executing, but if it exited, it's not executing anymore, it's terminated. But the operating system can't completely get rid of it. Its process ID is still around, and it's waiting to be acknowledged by its parent. So that's why it's called a zombie, because it's neither alive nor dead. It's kind of in between, like, you know, a zombie. So what's that acknowledgement look like? Oh, yep. Yeah.
So the PCB remains in both states, both processes, right?
Yeah, so in the zombie state, the PCB will remain around, but that process will be terminated. And in this state, the orphan process is still running, but we don't know essentially who its new parent is going to be. Yep.
So two questions. First one is, why does the child's ID still exist even after it's been terminated?
So it needs to be acknowledged by its parent still. Yeah, so the question is, why does it need to be acknowledged? Because if you didn't acknowledge it actually ended, how will you ever tell that that process has finished, right? So it might be the case where you might think that, okay, I'll just constantly pull its process ID over and over again to see if it's still running. Well, if there's not some acknowledgement, what might happen is your child exits and you look at it, its process ID exists, you think it's still running, and under your feet, the operating system goes ahead, because that doesn't exist anymore, creates a new process that got the same ID because it's no longer in use, and then suddenly you think it's still alive, but it's a completely different process. So you wouldn't be able to keep track of it without something like this.
And then my other question was, so if the parent exits first, then that ID would also stay alive because it would be the child of someone else.
So if the parent exits, the parent process ID might get cleaned up because it might get acknowledged by its parent. Mm-hmm. Yeah, so there's grandparents and all sorts of stuff. So we'll see an example. So how you do this acknowledgement, it's another system call, and it is called wait. So wait has the following APIs. So wait takes a status, which is an address to store the wait status of the process. So it will go ahead and write some information to that. It is basically an integer, and it will return the process ID of the child process, which is now dead. So if it returns -1, it means there was a failure, you don't have any children or something like that. If it returns 0, well, this call will actually block and wait by default for a child to die if it is not already dead. So there is an option to have what's called a non-blocking call, so it would return immediately and just tell you whether or not that you have a child that needs to be acknowledged. And if there is a child, it will return greater than 0 to tell you the process ID of the child that you just acknowledged. So that the information it writes to the address you give it has a bunch of information, including the exit code. So you can type man wait, find all the macros, because you're going to need a macro to query each individual status. So it'll be things like, hey, did that process exit? Was it killed some other way? Which for now, we just think that processes can exit, but soon enough, we'll see other ways for a process to exit. And then if you want to wait on a specific child process, there's a system called wait PID, so you can wait for a specific process to die. And it has to be your child. So this is what the example looks like. So let's go over this case, because now, yeah, it has forks. So we have main, okay. Main starts executing, we have a single process, and then immediately it forks. It returns a process ID. For the parent, it's going to get the process ID of the child. For the child, what process ID is it going to get? 0. So here we just check if there's an error. Otherwise, if we are the child process, we'll go to sleep for 2 seconds. And next, in the parent, we will call wait. We'll just have a print statement that calls wait, define a integer on the stack, and then call wait with the address of that integer. So wait would write information to that so we can read W status. So we immediately call wait, and wait should not return until my child exits. And here, my child should sleep for 2 seconds and then fall outside of this else, and then return, and then that process would exit. So the child process should just exit after 2 seconds. So now in the parent, I wait. So this should just block until my child actually exits, which should take 2 seconds. And then it should return the wait PID of the child that exited. Well, I only have one child in this case, so if it returns, it's hopefully the one I created. And then I use this macro here. So there's a W if exited, so that will tell you if the process has exited. And if the process has exited, you are allowed to use this macro to read its exit status. So I just print wait return for an exited process, what its process ID was, and then what its status was. So if I go back to it, oops. So if I do that, I just see calling wait, waits for about 2 seconds, then it says wait return for a process, gives the process ID of the child that is now dead and its status. Yep.
Could you explain again what W status does, or yeah, W status does?
Yeah, so W status is just, it just writes a bunch of information to an integer, like 4 byte, and it's formatted in kind of a weird way. So it'll write information to it, so you give it the address of the integer you want it to write to. So it will change this value, and then to decode the information from it, they have a few macros that check which bits are which, and it will tell you things. So that's why you have to use the macros. You shouldn't use it directly. So, yeah.
Sorry, this might be dumb, but how does the parent know, or like any else statement, how does it know which process it's waiting for? Like you have line 18 that says wait PID equals wait, and then you gave the
Yeah, so wait without any arguments will return as soon as the first child dies, or as soon as the first child terminates.
so, and it knows because in this process it created a child,
Yeah.
and that's all because of the fork earlier. So it knows that it's waiting on that child I created.
Yeah, so if I created 2 children, wait would return whenever the first one exits. Just the first one. So if I want to acknowledge both of them, I would have to call wait twice. Yeah. Yep.
So you said we don't want to like poll to see if the process ends because that's like bad use of resources.
Y-
But isn't wait just polling to see when the child ends?
So the kernel is smart. It can do it essentially using events, because that process will have a system call, and then it can just wake it up immediately. It doesn't have to pull. The kernel wouldn't have to pull for this. So if you do want to pull, like I said, there's a version of wait. You can say no block, and it will essentially do the pulling for you if you want that.
Okay, so wait isn't doing pull.
Yeah, wait doesn't pull. Yep.
What happens if there are no children, then what does wait return?
Yeah, that's a good question. What happens if I don't have any children? What does wait return? We can go ahead and just try that. So wait, let's do it again. Yeah. Equal wait. I call it wait example. So I have to wait for my child to die, and then I called wait again. So this will print the latest up-to-date one. So I got -1, which means I got an error message, an error code. So if I actually read into the error code and whatever it was, it's going to be an error code that says, hey, you don't have any children. Why are you calling wait? The kernel knows how many children you have. So if I call wait, I create one child and I wait twice. Well, the first one's going to work, and then the second one's going to be like, you don't have any children. What are you doing? Yeah.
In this context, returning 0 and exit 0 is the same thing?
Returning 0 and exiting 0. Yeah.
So how does the first child die exactly?
So returning from main, that number you have is the same as calling exit with that number. It's the same thing. Yep.
So this might be a little unrelated, but that's how like maybe JavaScript async works under the no wait stuff.
So JavaScript async uses threads and does things. It's basically threading for people that don't want to deal with threads. We're going to have to deal with threads later. So we can get into how async would kind of work, but it's basically threads you can't see. All right, so anything else for that? Hopefully that's, yep. So the macro functions. So it's just that this W status number, it has a lot of information on it that records everything about how that process terminated. So you just kind of have to look up the documentation to what they are. For now, all we need to know that this is essentially the only way we think a process can die right now is if it calls exit. So that's what this macro is for. And then if you read the documentation for W exit status, it'll be like, this is only valid if this is true. If exit is true, then I can read the exit status. So it's just one of those things you're going to have to read some documentation for. But for now, exit status is good enough. And yeah, so we're going to have lots of wait examples. So wait will wait for one of your children. Whatever the first child is that terminates, wait will return at that point. And then it acknowledges your child. So whatever it returns from wait, and that I got that process ID. Let's see. So it calls wait, in which case wait is going to wait for the first child to terminate. In this case, this process only has a single child. And whenever wait returns, that process ID can now be recycled. So if I tried to like go here and look up in proc or whatever, that process ID wouldn't exist because I waited on it, I acknowledged it, it's donezo at this point, completely deleted from existence. If I looked up that process ID before the wait, it would have already existed, and we'll actually do a quick example on that. So let's quickly blast through some other examples real quick. So let's explain what a zombie process is. So a zombie process is a process that is just waiting for its parent to read its exit status. So it's kind of like that in-between alive and dead thing I talked about. So that means that child process is terminated, it called exit, it's not running anymore, it can't run anymore, but it hasn't been acknowledged yet. It would still have a process control block. Another way to think about it is that process may have had an error in it or something like that. So you want to definitely make sure that, hey, you know, what happened to it? I need to read its status so I can figure out what problem it had. Another thing that can happen when we get into it in the next lecture is the operating system can essentially generate its own interrupt to the parent process that say, hey, your child is now dead, so that goes with your polling thing. So there's another way to essentially have the system generate an interrupt to say, hey, one of your child is now no longer with us. Please acknowledge it. But this is just a suggestion, and you are free to be a very bad parent, and you can just ignore it if you really want. Like, you're controlling what calls you make. The operating system can tell you should call wait, and you can just ignore it. And what the operating system does, well, it still has to keep it around until it's acknowledged, and then if the parent acknowledges it, then the zombie process just needs to wait anyways in order to be reparented. Eventually, it will become an orphan as well, and we'll get into that. But first, let's see the zombie example. So, in the zombie example, we fork. We're going to do the same thing where we create a child process. So checks if there's an error. Hopefully there is not an error. In the child, we're going to do the same thing where we sleep for 2 seconds and then we just let it return. So in the parent, we're going to do something a bit different. So in the parent, we're going to sleep for 1 second and then read the child's process state, which it will still be alive after a second because it takes 2 seconds, but it's sleeping. So I just wrote this function that will just read its state. So we can read its state and print its state and then check if there's any errors. Hopefully there will not be any. Then the parent is going to sleep for 2 more seconds, so it's going to wake up from here after 3 seconds. And then at that time, we know our child is now dead. So we'll read it again, and if we read it again, we should read that it is in a zombie state because we're the parent, we never called wait, so you can see that, hey, it was sleeping after a second, and then after 2 seconds, it's now a zombie. So that is an actual state. I didn't lie to you, it says zombie. So that means its process control block still exists. I didn't call wait on it. Yep.
If in between, like after the child dies, another process gets assigned that child's process ID, what would the child process state be?
So in this state, so the question was, hey, if in between those two things someone else got the child's process ID, what would happen? So technically, the child's process ID, it's still active because it's still a zombie, so no one else would get its process ID. It still has its process ID. It wouldn't get cleaned up until after it's acknowledged, and then it gets cleaned up. Yep.
Print state is a helper that you wrote.
Yep. Yeah, print state is just something I wrote. But it's going to open that proc file system, look at status, and just print the state line. Okay, so the funner one is the orphan processes. So an orphan process, it doesn't have a parent anymore. The kernel is very strict about the parent-child relationship. Every process needs to have a parent. So if your parent is now dead, you need a new one. So because that child process would still exit at some point and still needs to be acknowledged, so this reparenting process, well, the default parent of every single process on your machine is init. So by default, if the parent dies, it will get reparented to init, and that is why I don't think it happened this lecture, but sometimes when I ran that example, we saw that the child's parent process ID was 1. Well, that was because it happened that the parent died first, and it got reparented to init. So init is like, you can think of it as like the orphanage or something like that. Process ID is 1 is the orphanage. If anything needs a new parent by default, it goes up to them. There is a feature in Linux to designate another process as an orphanage, but it has a fairly gruesome name. Its gruesome name is called a sub-reaper because it is meant to reap the zombies and kill the zombies. And technically, a init, orphanage is a nice way to put it. Technically, a init is called a reaper, like the Grim Reaper. So those are the naming conventions that they have decided. Don't blame me. So here is an example of an orphan process. So same thing, I'm going to fork immediately, create a child. In the child, I will just read my parent's process ID, and then wait 2 seconds, and then read my parent's process ID. So my child reads its parent, sleeps for 2 seconds, reads its parent again, and then finishes. And then in the parent, it will just sleep for a second. So for the first one, its parent should still be alive, and then in the next one, it should get reparented. So if I go ahead and run that, I'll see that, hey, I have my parent, and then my parent dies, and it actually returns to my terminal, because guess what? When you type commands in your terminal only cares about the process you typed, so when the parent's dead, you get control back and you can type again. So that's why the terminal looks like that. But I can see here that after the sleep, I can see what it got reparented to. It got reparented to 1, like I said. So you can see this, and that's an orphan process. So now it's no longer an orphan. It got reparented to a init, and now it has a parent again. Everything is right with the world. Any questions on that? Yep.
Sorry, so why does which means say after the fork, this is a bit backwards, but then after the fork, the parents and the child run at the same time? Because let the parents die first.
Yeah, well, in this case, the child prints something, sleeps for 2 seconds, and then prints the parent again. And the parent just sleeps for a second and then exits.
Yeah, but which means, but you still have to have a process that runs before another one, right? Say, if you ran the parent first, how would the first print line of the child still print its parent's ID?
So, yeah, the question is, if the parent ran first, what does it matter? So the sleep, computers are really fast. Sleep for a second is like an eternity. So no matter what ran first or whatever, so if the child ran first, well, it would do the print line immediately. If the parent ran first, it would have slept for a second anyways, and then your kernel would say, oh, I could run the child, and it would run that print line and then go to sleep. So
What if the parent dies before the child process gets to?
So there might be a situation if the child doesn't run for a whole second, but that will ultimately never happen on any computer because they're like a second is, they can do so much execution. So there is like a 1 in a trillion possibility, but in reality, that's not going to happen. Yep.
Sorry, can you run that again?
Yep. So,
You have a print statement and then sleep for 2 seconds and then print, but then you said if the parent exits, that child process, I guess that's what
yeah, so I got the first print statement. Oops. Here, I'll run it again. So I got the first print statement there, and then I can see my terminal came back because after a second, the parent died, and your shell only cares about what you executed.
Oh, okay, so that's why it's like that.
Yeah.
I was confused by it.
Yeah, so this build orphan example was the thing that called main. So in the context of the program, it's the parent. So after a second, it dies, and then I can get my shell back and type on my shell because as far as my shell doesn't know that the process I ran also created processes, right? So it just cares about what you typed. After a second, I can type back on my terminal, but that other process that got reparented to a init is still running, and whenever it's doing printf, it's going to go to the same terminal. Yep.
Is it possible that you have a child that might be long enough and interact with the terminal, mess with another
Yeah, so your question is it possible that I launch a child and it starts messing with my terminal
Like
after the parent?
say we run a program to start and say sleep was like for the child was like 20 seconds or so. And then I ran another program in my terminal for another parent that say had scanf in it as well, stuff like that. Meanwhile, my child from the other program is still running.
Yeah, so there's a question that if I have two children that were created at two different times, will they interfere with my terminal, I guess? So the answer to that is kind of. So we'll get into that in the next lecture because we're going to talk about IPC in the next lecture. So we'll cover that in the next lecture. Yeah.
Just a really simple example. You just increased the child sleep time, and then you ran the entire thing again. Then, like, because you get your terminal back, right? You type again.
Yeah.
But the child's not done yet. So then, so then theoretically, you should see like 2 parent exits before the child.
Yeah. So you say I just increase my time there and then run a bunch?
Yeah.
Yeah, so if I run a bunch here, I get my terminal back after a second, and I can print another one, and then I should start seeing some return values from all the children. So yeah, that's what's happening. So I ran it 3 times, I got my 3 back. Yeah. Yeah, so your terminal output, for input it gets a bit trickier, but for output, they'll just all use the same terminal that they were launched on, even if they get reparented. Yep.
Will it then automatically call wait for this, like all children really parents to the net?
Yeah, that's a good question. So will init automatically call wait PID? So that is actually the second and only other mandatory job for init. So it launches processes and then it calls wait. So if you look at the source code for, we'll look at the source code for a educational operating system, but if you look at its init implementation, it forks and then exec_VEs a shell, and then it goes into while true, wait. And then it just waits for things to get reparented, acknowledges them. It's just an infinite wait loop at the end. So that's like, so now you could implement init. You know the 2 things it actually does now. All right, any other questions? All right, cool. Well, let's see more fork stuff then. Real quick. So someone asked, hey, well, how would this maybe be useful? So if we wanted to, we could write a process like this that spawns lots of child processes that hopefully do something. So in this case, I have a for loop that goes 1 all the way to 4, and each time through it, it's going to call this new process function. And in the new process function, it can fork and then see if PID is greater than 0, that means it is the parent, and it could just return immediately, and it would have created a child. And then here, I can say, oh, check for errors, and otherwise, I could have a process that loops 0 to 10, and then this represents it actually doing some useful work. So if I go ahead and run something like this, well, I should be creating 4 processes, and each of those 4 processes are doing 10 things. And if I have more than 1 core on my machine, I'll probably see them interspersed, and they'll be all working at the same time. So if I run that, well, it's really fast. I see that between them, they all do 0, then they all do 1, then they all do 2, then they all do 3, then they all do 4, and not necessarily in the same order every time. So for 3, it did 2, 1, 3, 4, then it did 1, 2, 4, 3, and that's all up to the kernel when to actually schedule them. But you could do something like this to split your task into like 10 things. And in this case, you can answer questions like, how many children do I have? How many children did I create there? here, let's, 4, right? So I created 4 children. What didn't I do? Was I a responsible parent? Absolutely not. So this program, I should probably improve it a little bit. And anyways, that's time. So just remember, pulling for you. We're on this together.